Part 2. All right, so this is Chapter 6, Thermochemistry. We're going to have a little fun with heat today in the lab, too. I think we left off, I had it marked 46 was the next one. Finish this one off. All right, get that out of the way so I can see what I'm doing. Based on the above reaction, what energy change occurs with 1.2 moles of methane? All right, so we've got this. Methane is reacting with chlorine, okay, and producing carbon tetrachloride. Yep. And what? HCl. Is that aqueous? I think yes. Well, that's hydrogen chloride. And the delta H for this is negative 434 kilojoules. That is a very energetic reaction. I wouldn't want to use a lot of that in the lab. Scale it way down. Do it under a hood. So what's the question? 1.2 moles of methane. And the question is, how much energy is released? What energy change? Now, when they say energy change, that means it's supposed to mean, oh, okay. Instead of a sign, they say released or absorbed. Okay. So let's see what we got. 1.2 moles of methane. This value is for this equation as balanced. So since it's referencing methane, it would be minus 434 kilojoules per mole of methane, because there's one here. So 1.2 moles of methane. And then we say minus 434 kilojoules per mole of methane. That way we cancel this part and leaves us with kilojoules. So that would be, let's see, 1.2 and 434 minus 521 kilojoules released. So that's the word you're looking for. Released means exothermic.
If you transfer that to joules.
Oh, that's right. The answers are in joules. Okay. I find the easiest way to do this is to substitute for this into the third. And that gives me 521 joules. And then if it's in, scientific notation, I would just move these two over and store that 100 over here. Minus 5.21 times 10 to the 5th joules. Well, I got an extra. Yeah, that's right. They're right. I'm only allowed to, let's see, this would be, excuse me, better put that 0 there. This would only allow me 2 significant figures. So 5.2 times 10 to the 5th released is A. Okay. 46. Let's see, who's next? 51. Okay. Specific heats of metals. If the same amount of heat is added to 25 grams of each metal, which are all at the same initial temperature, which metal will have the highest temperature? All right, when we say here we focus on the units of measure. Right? Specific heat is in units of measure of joules per gram degrees C. That means for every joule of heat absorbed by the material per gram of the material, every joule per gram of the material, the temperature will rise 1 degree C. So if the specific heat is very high, it will absorb a lot of heat before this goes up a degree, the higher the specific heat. So the question is, if they're all the same 25 grams of each metal, which are all the same initial temperature, which one will have the highest temperature? The one with the smallest specific heat, right? Because it will move. The mass is taken out of the picture because they're all the same. So the temperature will move more for a smaller value of specific heat for every joule that you add. The smaller value will give you the greater change in temperature. And think about that in practical terms. Think about water versus, I don't know, a block of iron. If you apply a certain amount of heat to the iron, its temperature will change a lot. But if you apply the same amount of heat to water, it won't change much. Water has a very high specific heat. So the lowest one in there is lead, is it not? Yeah, lead. Lead will have the greatest change in temperature. The delta T will change the most for lead. We could look at it with our formula also. Right, specific heat times mass. Is that right? Oh, excuse me. What am I doing? Q, I was thinking of something else. Is change in temperature times specific heat times mass. Right? That means change in temperature will cancel this one, and mass will cancel that and leave us with left over with joules. Okay, so the answer is lead for that reason. Let's see, I skipped over a bunch of these where the A, B, C's, and D's. They just, when I can, I skip over those because I want real world, not this imaginary stuff. Let's see, where is it? Oh, here we go. All right. Okay, we're going to use Hess's law. I better put this way over here out of the way. And our target equation, I'm going to put it at the top. P4O10. P4O10.
Mm-hmm.
Yeah, solid. Plus 6 PCl5. And that's a gas. Yields 10 Cl3PO. Yes. And we're looking for the delta H under standard conditions for this one. Based upon any combination that is permitted of equations 1, 2, 3, and 4. All right. So let's just take them one at a time. P4O10. Who has P4O10 in it? Equation 2, right? Okay. So equation 2 has P4O10 in it. Only it's on the wrong side. So can we save some time and just flip the equation? Let's flip it. P4O10 on this side. P4O10 on this side. And I'm gonna line up the arrows. P4 solid plus 5O2 gas. Now, what does that do to the enthalpy? It just reverses the sign. So it'd be plus 2967.3. These are all in kilojoules. Yeah. Okay, so there's your first one. And we got that one taken care of and that one with this equation. PCl5, who's got PCl5? Roman numeral 3, and it's on the wrong side. So PCl5 should be on this side, and then PCl3 and Cl2 on this side. Okay, and we need to reverse plus a 4.2. That's not the only problem. We need 6 of these. So we got to multiply the whole thing, including the enthalpy, by 6. We'll need to put another 6 over there. Okay, so that means we'll have 6 PCl5 equals 6 PCl3 plus 6 Cl2, and then 6 times 84.2. Do that again. I think my fingers slipped. There. 505.2 plus 5. All right, so far we're using this one and this one. All right, now how about this one? Cl3PO. Cl3PO is the last one, and it's on the correct side, only there's not enough of them. So 4. And I saved some space by doing this. 10. PCl3. PCl3. I'm going to go ahead and multiply it by 10 because we need 10 of those. Right? We're looking for Cl3. Yes. 10 of these. And then 10 times a half O2 would be 5 O2s, wouldn't it? 5 O2s. And then we multiply 10 times that value. We didn't flip the equation. I need to put fewer things in my pocket. So 10 times minus 285.7 would be that, correct? I went ahead and multiplied that one by 10 so that, let's see, we've got this one matched with that one. We got this one matched with that one. Okay. Now, what we need to do is see, are we left with anything that's not supposed to be up there? All right, and the answer is yes. We've got oxygens, well, oxygens cancel. But on this side, you get 5 O2s, and that side, you get 5 O2s. So that's good. And on this side, you have 6 chlorines, but nothing to cancel them with. And P4 with nothing to cancel. So we got to look for P4 and Cl2 on this side. Right? We're trying to remove those from the calculation, from the combination. So that's where number 1 comes in. We've used 2, 3, and 4, so 1's going to be in, and it's got P4 and Cl2 on the left-hand side. Oops, I circled the wrong one. We're using this one. There we go. Okay, so if we go back to 1, it looks to me like P4 solid plus 6Cl2 gas yields 4 PCl3. Mess me up. It is going to mess me up. I must have done something wrong. PCl5. Let's do PCl3 and Cl2 needs to be on. Now, why is that not working? If we put this in here just like it is, minus 1225.2. No, 0.6. Am I looking at it wrong? That's good. This is going to take that one out, right? 6Cl2 is going to take this one out. And that leaves 4PlC3, 10 PCl3. Did I read the equation wrong? No. So I'm going to end up with that and this extra. Was there another one in there? PCl. Yeah, there's PCl3. But they're already being used. Huh. All right, let me see what I did wrong. Because I've done this one before. I don't know why it's not working. 40, 59. Okay. So 2. Got 2 up there. Yep. And then I did 3, 6, 6, 6. Yep. And then I did 4, 10 PCl. I go 2, 10. Okay. Okay, what I did next was, before we tried to do this one, I brought all of these down, these 3 down. So let's do that. Maybe I can see where my problem is if I do that. So rather than, I'm going to bring down everything that's crossed out also. So P4O10, I'm not going to write the phases in there because they get jumbled up. 6 PCl, 5, 10 PCl3. Oh, that's where it is. Okay, I can see the problem already resolving itself. And then this one we have P4, 5O2, 6 PCl3, 6 Cl2 plus 10 Cl3. Okay. Keep this one. Keep this one. And NPCl. Okay. This one we're going to deal with. P4. This one we're going to deal with. This one we're going to deal with. 6 PCl3. This one we're going to have to deal with. We have to deal with all of these. Keep that. Those are the ones we want to keep. And 10 PCl3. Where's my 5? Oh, 5 oxygen. That one. 2. Okay. So the oxygens cancel. And then we put in number 1, which has P4 on this side, P4 6Cl2 plus 6Cl2 yields Cl3P, 4 PCl, 4 PCl3, or 3. Okay. And the value for that was minus 285.7.
Value of that was 4.6.
Thank you. There we go. Okay, now if we add these together, we've got 10 PCl3 here, we've got 4 plus 6 there. Those cancel. Cl2s cancel. And P4s cancel. There we go. So now we kept, I didn't mark this one out. Yeah, that one marks out. This one, and that one we keep. So now what we can do is add up this one, this one, this, this. There we go. So I was seeing a problem that didn't exist. Where'd you have to go?
My GPA is a little messed up because I did fooled around the first year of
Oh,
college years and years ago. I just found out more stuff, but it's about tutoring too, and it turned into a whole bunch, and I'm trying to get academic forgiveness. On some classes I messed around with years ago.
okay, so let's add those up. 2967.3. Yep, and 84.2. Oops, nope. 84.2. 505.2. And 2857 minus. And 1225.6 minus. Okay, I get minus 610. Is that one of the answers? Yeah. So altogether, this is minus 610. So I was creating a monster where there wasn't one.
Yeah, you lost it.
Yeah, I mean, did you follow me through this progression through here?
Yeah,
Okay. So then, what I needed to do was bring everything down from this one, and that one, and put it in a line, cancel the stuff I could and see what needed to be dealt with. And then we went to number 1 and put in that one, unmodified actually. And it allowed us to cancel that term, these terms, and chlorines, those terms, and the PCl3 from here to here. All right, that was a bear. I made it worse than it was actually. Let's try 68. Choose the correct equation for the standard enthalpy of formation. Okay, this one was better behaved. Need to clear the board. I think I thought I was getting a good deal, but I ended up with these tiny ones. I just bought them, so I have to double them up. They still have magnets in them though, so that's okay. And they're fresh, so they erase better. Maybe they're meant for grade school whiteboards. Or those portable ones, I bet that's what they're for. The little ones. Okay. 68. All right, when you're asked for the enthalpy, standard enthalpy formation, you start with the product. Correct equation, standard enthalpy formation for carbon monoxide. So you start from here in its standard form at standard temperature and pressure, 25 degrees Celsius, 1 atmosphere. It will be a gas. Then you work your way backwards to the individual elements under their standard conditions. And the standard for carbon is graphite. Okay. And then oxygen. And oxygen, elemental oxygen under those conditions is actually diatomic. So what we have to do is take half of that to give us 1 oxygen. So you start from the standard enthalpies of formation, you start with the product and you work your way back and do whatever you have to make it fit. And then minus 110.5 is the delta H. Kilojoules. All right, so what's that, C? Yeah, that's C. Please. 58. And 78. One of the main advantages of hydrogen as a fuel is that, well, let's see. We got 5 selections and we don't have any oddballs in there, like none of the above or 2 of the above. The only product of hydrogen combustion is water. That's a good reason. Right? If you burn hydrogen and oxygen, yield water. Right? So you need 2 of these and 2 of these. That's perfect. Right? At least for the carbonistas. Right? They don't want carbon emissions. That's a good one. It exists as a free gas. That's no advantage. Lots of fuels. Methane exists as a free gas. It can be economically supplied by the world's oceans. It can be supplied by the world's oceans, but economically not yet. In order to do that, you need a cheap source of energy that is non-polluting. Right? It doesn't produce any carbon. And that's not what we have these days. What they need is nuclear power. That will produce all the energy you need to split the water molecule. It's just this reaction in reverse. You take water from the oceans, split it into hydrogen, oxygen, and then do what you want to with the oxygen or blow it in the air. Doesn't matter. And bottle that. That would be economic if we had a cheap, non-polluting source of energy. Plants can economically produce hydrogen needed. Nope. Plants typically take carbon dioxide from the air, water from the air, and make carbohydrates. They start off with simple sugars, and then they build from there. So that's not it. Contains a large amount of energy per unit volume of hydrogen gas. It contains energy per unit volume, but whether or not they're not giving us enough information to compare it with other sources. Right, large amount of energy, I don't know. So we have to pick the best one. And the best one as far as advantages go is its product is water. I saw a report, when was it? Yesterday, I think it was. Airbus, everybody knows Airbus. That's the European consortium of companies from different EU countries that produces a product that is in competition with Boeing primarily. And they're in the process of developing an airplane that will fly on hydrogen in their jet engines, and to modify the engine to burn hydrogen. I don't know if they'll succeed because they can have the plane, but they don't have the infrastructure. So we'll see where that goes. If they want to spend the money on it, then more power to them. Which of the following is not being considered as an energy source for the future? All right. So A, B, C, D, and E. How about ethanol? That's my abbreviation for ethanol. Yeah, ethanol is always considered. I mean, we've got most gasoline we buy now has 10% ethanol in it. In some places you get even higher. Methanol is also. That's probably better than ethanol for security reasons because you can't drink methanol. Seed oil, yeah, that's also being considered. Shale oil, oh, definitely. Shale oil requires fracking to get it out. And carbon dioxide as an energy source, I don't think so. Carbon dioxide is the product. Right? And we'll learn when we get, let's see, are we going to do that this semester? We're going to no. Next semester. We'll learn about formal charges, oxidation states, and the ones that, well, I don't want to go into too much detail because that'll ruin it for you. Carbon dioxide is a product. It's not a fuel. Let's leave it at that. So E is the answer. It's the one that's not being considered as an energy source. All right. And we got some of those fill in the blanks in there. How about this one? 90. Okay, a gas absorbs 188 joules of heat and then performs 310 joules of work. And the change in internal energy of the gas is what? Okay, we need our definition of internal energy. It's heat plus work. So if the gas absorbs 188 joules, that means it's positive value, right? Everything is referenced to the system. The gas receives that much energy, so the heat is plus 188 joules. How about work? Then it performs 310 joules of work. That's negative. If it performs work on its surroundings, it's losing that work from its internal energy. So that's, what was that again? 310. Yeah, 310. So we subtract the two, right? 1, 2, 2, is it? 10, and 1. Right, yeah. Joules. So it's negative. The change in internal energy is negative 122 joules. Okay. And next, we skipped a bunch of them. All right, 99. Let's see, nitric acid, HNO3 was first prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3. Okay, and the equation is below. Calculate the delta H for this reaction. Okay, that's fairly simple because we have the heats of formation. So if we go by our equation, sodium nitrate plus sulfuric acid, I think they said, yields sodium bisulfate. That's the old wording. Sodium hydrogen sulfate is proper these days. Plus HNO3. Oh, I better put those. The standard heats depend on that. Liquid and solid. Okay. So if we're going to calculate the heat of formation, the heat of this reaction, we'll use the formula where we take the standard heats of the products, right, of the products, and subtract the standard heats, summation of the standard heats of the reactants. Okay. And since they're all, this is a balanced equation, they're all 1, 1, 1, 1. We don't have to multiply the moles, but if you had a coefficient in here somewhere, you would have to take that value from the table and multiply by the number of moles. Okay, so in this case, standard heats of products. So sodium bisulfate is minus 1125.5. Is that kilojoules? And assume I've already multiplied times 1 mole of each. All right, so that one, and then the next one is nitric acid, which is minus 135.1 kilojoules. And now we subtract the reactants. Saltpeter, minus 467.8. Okay, and then let's see who's next. Sulfuric acid, just 4, minus 814. 80. There we go. So that should be the delta H for this reaction under standard conditions. So 1125.5, 135.1. And then this becomes positive and that becomes positive. 467.8 and 814. So I get 21.2 kilojoules for that reaction. Positive 21.2. Okay. Alrighty, that was it.